Hi, my name is Seema. This is my Module 2 presentation. So first, I just kind of want to introduce the data, and to do this, I'm going to use the describe function. Looking at the data here, we have 10 x values. We have a column differentiating between sex, and then we have two y columns. We are seeing mostly negative means regarding our x values, and then we see a moderate standard deviation, and then a moderate to strong skewness, leading us to conclude that our distributions are not perfectly symmetrical. And for our y's, our y1 and y2, we kind of see a similar pattern where the means are negative and there is some skewness as well. So here we're going to be looking at correlation and covariance. So firstly, with covariance, we have a covariance matrix of the data. The covariance measures the direction of the linear relationship between the two variables. A covariance matrix like this can be used to examine the pairwise covariances between the variables. So if we look diagonally, so for example, like if we look at x1, x1, x2, x2, x3, x3, then we can see that we can see the covariances of each variable, and then if you look off diagonal, then you can see the relationships between the variables together. So like x1 and x2, x2 and x5, for example. So let's first look at the diagonal. We do see all positive covariances, and then the higher the variance, the more spread out the values are going to be for that variable. So then if we look at the off diagonal covariances, we do see some negative values kind of sprinkled about. And so let's, for example, look at x1 and x2. They have negative covariance, so that's showing us that as x1 increases, x2 will decrease, and then vice versa. Obviously, they have that inverse relationship. And then there are two things that we're looking at regarding covariance. First, there's going to be that positive or negative value to explain the direction of the relationship. And then we're going to be looking at the magnitude. As I mentioned before, the larger the value, the stronger the relationship is going to be. And we also see here that x5 has the largest variance of of 0.8229, and then x2 has the smallest variance of 0.5333. And then our next, let me get my laser pointer. Our next table here is regarding correlation. So correlation is the measure that gives you strength and direction of the relationship between two variables. So a positive or negative one indicates a perfectly linear relationship. And then if you have 0, then it's going to indicate no linear relationship, sorry. So between covariance and correlation tends to be more informative because it standardizes the relationship. And so again, we're kind of going to look at it versus diagonal and then off diagonal. So here on the diagonal, we do see that all of them are positive 1.00. So we can see that there is a perfectly positive linear relationship. And then the off diagonal elements are going to vary. So for example, if we look at x1 and x3, we have a value of 0.645, and that informs us that there is a moderate to strong positive correlation. So as x1 increases, so does x3. And you can see that like for example with x6 and x3, there's a bigger number of 0.761, and then that'll mean that there's a stronger positive correlation than the x1 and x3 had. So the relation, and then just to give an example of a negative correlation, it would be like x8 and x10 have a correlation of negative 0.364, meaning that it's going to be a weak negative correlation because smaller number. Okay, so next is going to be reliability. Reliability is the extent to which measurements are repeatable, and any random influence that can lead to measurements being different is going to be considered a source of error. And reliability is expressed using Cronbach alpha or the standardized alpha. So Cronbach alpha will take into account the differences in the item standard deviations, whereas the standardized alpha is typically used if the item standard scores are summed to form scale scores. And then here we can see the raw Cronbach alpha being 0.29. So this is a relatively low value, leading us to conclude that there is poor internal consistency. And then the standardized alpha is taking into account the variances of these items. So it is a little bit higher here, but it's still relatively low. So we're still going to come to that same conclusion of poor internal consistency. So then underneath that, we have the 95% confidence intervals of Cronbach alpha, which gives us a range of values that the true reliability of the scale will like fall between. So here we have a matrix of the reliability if an item is dropped. So we can see how the alpha will change if we drop an item. And the reason this is important to see is because it can help us see what items should be eliminated in order to have like the highest alpha we can. So for example, here we can see X2 shows a raw alpha of 0.506. And we can see that if we eliminate our X2, our alpha will go from the 0.29 here to the 0.56. So that's a big difference. So that can lead us to see like, oh, maybe there's something problematic going on with X2 and we should eliminate that. Our next matrix here is this item statistics. This section is just illustrating the statistical details for each item. We can see X1 has a high correlation of this 0.73 or yeah, hold on, the standard, yeah. Or I'm sorry, it's the raw, we're looking at the raw.r. So it's 0.72. So this is considered a high correlation, whereas if you look at X5, you have the negative 0.41 value, which is much smaller. So you can kind of see which ones you would keep versus eliminate here. And from this table, I would conclude that X1, X3, X6, 7, and 10 would survive the item analysis here. All right, the last matrix I have here is just showing the frequency, and it's basically just telling us like how many people are selected each response category. So for example, you see for X1, 37% selected the negative 1 response. I'm sorry. So basically the main takeaway of these matrices was to show the low reliability because of the low Cronbach alpha and the fact that we can adjust it by seeing these different values and kind of get better results in a way. So lastly, I just kind of want to touch on this histogram here. It is displaying the raw alphas, and you can see that the alphas like can change if you drop an item and regraph it. And then you just see this red line here, which is showing the alpha for the data as a whole. So next is validity. So we are going to kind of look at this like stepwise. So first we're going to look at these residuals here, which are just the differences between the observed values and the predicted values from the model. And we have minimum, 1Q, median, 3Q, and maximum values that all tell us how well our model is fitting the data. And we do want these residuals to be symmetrically distributed around 0, but it looks like these are a little bit spread out. And then here we have our second matrix of coefficients here. And we can see it's kind of showing our estimate, our standard error, our t-value and then our p-value for the hypothesis test. So this is, the estimate is showing that the change in y1 for 1 unit increases in the predictor. So for example, like for the x1, the value is 0.130, meaning that if x1 increases by 1 unit, y1 will increase by 0.130 units. And then this basically just assumes that the other values are held constant. And then if we jump over to this t-value, this is just showing the ratio of the estimate to the standard error. And if the p-value ends up being less than 0.05, then we reject the null hypothesis. And then, so then if we're looking at this data, we can see that it shows a p-value for, like here, you can see the p-value of 0.5269, and this is greater than 0.05, which means the intercept is not statistically significant. We also see that x1, x2, and x3, basically x1 to x4, have p-values that are greater than 0.05, and some of the other ones too, but those are just some examples. And again, those would not be statistically significant either. And then the last little section on the bottom is just like this right here, is just a little key to help, like, it's just a key to interpret the significance, basically. And then down here we have the residual standard. The residual standard error is showing at 0.646, and this is just showing the average distance between the observed and the predicted values, and we want this value to be as small as possible, because the smaller the value, the better fit the model is to the data. And so we see a p-value of 0.02815, and that's just indicating that the model is statistically significant, because again, it is now less than 0.05. So that's where we got that. Okay, hypothesis test, specifically the ANOVA test. So this is comparing males versus females on y1. So you see a significant effect leading us to the conclusion that males and females differ on y1 significantly. And we can make this conclusion because we see a p-value that is much smaller than 0.05, so therefore it is statistically significant. And because it's smaller than 0.05, we reject the null hypothesis. Another point here is the F value on this matrix here. We have, this just measures, it's just the ratio of the mean square of the sex to the mean square of the residuals. We have that here. And here we get a F value of 51.4, which indicates that the variation between the sexes is greater than the residual variation. So that can help us explain the variation regarding like the dependent variable, and then we can say that there is a statistically significant relationship between the sexes. And then this value here is the Cohen's d value, which helps us kind of discuss effect size, which is just the difference between the two means. So here we have y1 of males versus y1 of females, and then that gets us this value of 2.62. And again, this is the Cohen's d value, and it's just a statistical value that kind of compares the average of the two groups. Okay. Next here, we're looking at two different kinds of t-test. So this one here is the Welch t-test, and this is the priori t-test. So first I'm going to discuss this Welch test. So the Welch t-test is a two-sample location test, which is used to test the null hypothesis that has two populations that have equal means. So here we have, it's a little bit small, but a t-statistic of 3.389, which is telling us that the observed mean is 3.389 times the standard error, which is quite a large difference. And then we also see a p-value here of 0.022, which is, again, below 0.05. Therefore, we reject the null hypothesis and can conclude that there is a statistically significant difference between Y1 in females and males. Also, we can see here the confidence interval of 0.342 and 1.390. And because it does not include 0, it adds more evidence that the means are significantly different. So now moving on to this side of the slide, the priori t-test, the priori power t-test. So this is done to help kind of plan your study by helping you kind of know your required sample size. So it helps you make sure you have enough participants to detect a true effect and minimize the risk of your type 2 error, and kind of through doing that will help you avoid wasting resources. And then, so here we can see we got a result of here about, you can round up, it's about 64 participants that we need in order to achieve an 80% power to detect an effect size of 0.5 at the O5 level. So that's just what's this is showing here. So yeah, thank you so much for listening. And then I have my citations on the next slide as well. Thanks.